What I am drawing on your screen is about the story of a guy who discovered something and that he was so excited, he went out and finally that he even ran naked in town shouting the word Eureka, meaning I got it. I'm not telling you the rest of the story though, we are just going to focus on the one that he discovered. It's called buoyancy. The phenomenon where a force is exerted on objects immersed or submerged in fluids like that, in water, as in the bathtub here. This force is sometimes called buoyant force, but the most common equivalent term in international exams is upthrust. The details about this upthrust force exerted by fluids is summarized in a statement called Archimedes' principle. This guy's name was Archimedes. It was named after him. We are going to focus on that, the principle that saved this guy's head. He was actually threatened, going to be beheaded if he couldn't solve the problem. Some stories said, okay? Let's clear my screen a bit. Let's put all these here. And yeah, we focus on Archimedes' principle. As I was saying, imagine an object immersed in liquid or fluid in general. Anything that flows, which includes gases. Say Archimedes himself or any other object here, a force will be exerted on him. We call it upthrust, with magnitude equal to the weight of the volume of the fluid that has been displaced. We can write the principle as weight equals the force or the upthrust. Very important to note here that the weight is not the object's weight or Archimedes' weight, but the weight of the displaced fluid. Let me color it blue, alright, like that, there. Our displaced water. The weight of this water is equal to the force on the object immersed in water and is called buoyant force or upthrust. Upthrust. There we go. Now, since the weight may be very difficult to measure in cases like this, let us have a quick side trip, a recall of some ideas we know to simplify the principle so that we can do calculations easier. First is the density in symbol rho, this one, which is defined as the mass of an object divided by the volume of the object. In our case here, it is from the mass and the volume of this displaced water. Now, the other definition, the weight, operationally, this is equal to the product of the object's mass and the acceleration due to gravity, or sometimes called gravitational field strength, about 10 meter per second squared or 10 newton per kilogram. So the weight, which is this, we write it here instead of W, mg, and that the m here in the equation for density, when we cross multiply, we get an expression for mass. And we put that here, m is actually density rho times the volume. And then the g, or the gravitational field strength. And this one now is our formula in finding our force, rho vg, or as we call it, the upthrust, which is pushing an object immersed in fluid upward like that, the arrow. In most exam, hold on, let us free up some spaces on our screen first. Let's minimize this here. Okay. Now, in most exams, you would likely be asked, as per the syllabus, the reason why the direction of force is upward. The force is named upthrust. Take note of that. And also, what we did so far was to translate the Archimedes principle into a mathematical equation. Sometimes you will be challenged to show that the equation or equivalently the principle is correct. I mean, doing the reverse. Imagine that you do not know the principle and you do some kind of derivation that will lead you to the principle itself. Okay, part of this video is on that. Let me arrange this a little bit, taking up lots of spaces. We start with the recall of what pressure is and derive the principle from there. The symbol for pressure is P, equal to F over A. F is the normal force perpendicular to the surface. That is what is meant by normal here. And A is the area where the normal force is being applied. Pressure depends on two quantities. Let's put this here a little smaller. And as a quick example, say you have a uniform box here with these dimensions like that. All right. It exerts a pressure on something it is interacting with the force equal to its weight, okay, acting on this area. When we change the position, say this, okay, better this way, like that. Now, this is the area in contact now. By repositioning our object, changes the area where the force is applied, and therefore changes the pressure due to the change in area, even when the force remains the same. The formula applies to all, but usually very useful when dealing with solid. Archimedes' principle is about fluids, liquid or gas. So let's rewrite the equation for pressure with quantities easily measured in fluids. Okay, imagine here is the Earth, And this is me, Mr. Marlon, standing at some place close to the equator. Maybe better to flip it a bit, just for discussion, and I can get the feel that Southeast Asia is on top of the globe at this moment. Okay, like that. Okay? We all know that we have an atmosphere, a fluid, and that considering this area of my head, this one, you can easily imagine all particles above it straight up to the top of the atmosphere, this air column here. The force of the air column on this area on my head, putting pressure on me right now, by definition. The force is the weight, so we have this, P equals W over A, and that the weight is equal to mass times G. So again, we rewrite pressure equation P equals mg over A. Now, using the density equation, we get an equivalent expression for mass m here, equal to density rho times the volume of the entire air column above the area on my head. Then copy G here over A. This air column is like a cylinder, and that volume can be calculated by multiplying the area A and this distance from top of the atmosphere to my head. Let's call it H. Alright? So we can use this to simplify our equation even more by looking at this V over A here. So we then should have pressure equal to density rho, H replacing the V over A, then G. Alright, like that. Alright, so our screen is full again. Let me bring this somewhere here. Okay. Alright, let's continue. We haven't considered these yet. Alright. So now imagine that we have this fluid here. Imagine this was the water in the Archimedes bathtub. All spaces, blue, are occupied by water. You know that no two things can occupy the same space at the same time. So if we immerse an object in water, the water that used to be here makes the level of water rise. Alright, like here. Or if the container couldn't hold it, water will be poured out of the tub. Alright, like that. Here. Okay? Now this space, the volume used to be occupied by water, is now occupied by the object. Okay, and the object experiences pressures. Remember, pressure is dependent in rho, g, and the depth. The distance h measured from the top of the surface of fluid. Let's place P here to say we have pressure here and also here. But these pressures have different values because they have different depth or the distance, this h. Now imagine that these are our areas for the two pressures, and that we can say that the A here, the area, are the same. Okay, over A here and over A here also, same values, and here's the force. And now in order for the pressure P here to be smaller than the one below, the magnitude of the force should be smaller than that at the bottom. Yeah? Alright, now if we are to draw a free body diagram, maybe this one, this orange dot representing the object, we say that there is a force here acting normal to the object and a greater force here also acting normal or perpendicular to the object. Okay? So the general effect of the two forces is a resultant directed upward. The object is experiencing a force up, which answer our first question here. Why upward? Our force is an upthrust. Okay? Let me write what we learned here, alright? The force's direction or the upthrust is from high pressure, like in here, to the region where there is lower pressure. Force in fluids exists whenever there is a difference in pressure, like delta P in symbols. Let's put the dimensions of the objects in black, alright? Here and here also. And at this point here, we have a pressure different at this point here. Due to differences in depth or distance of the point from the surface of the water, HO here, let's call this one the other one. Let's call this other one HF. Now we can say that this delta P here is equal to the force that we found divided by the area. From here, let's see if we could end up having the Archimedes principle starting from our understanding of fluid pressure. So rearranging the formula here gives F equals area times difference in pressure. The difference in pressure here, I just use PF and PO to say that they are both pressures but of different magnitudes. We have PF here minus PO here, difference in pressure. Now each of these P's can be calculated using this formula, rho Hg. And so we have area A times the quantity rho HF for this pressure times the G minus rho, same value as we are dealing with the same fluid here, HO times G. Simplifying further, we got area times the common rho and G. When we simplify this further, we get area times the common rho and G and the difference between the two distances. This diagram, this HF minus this HO gives this dimension of our object, a distance H, this red distance here. And so these can just be replaced by that. Let's erase, okay, and just write H here. Now, if you have an A and an H multiplied, here in this blue equation, you get a volume. So we also replace this A and H here by just V, or the volume of the object or the displaced fluid if it is completely submerged in water or other fluids. Just to make you see that this is now the same as what we have a while ago, upthrust, is rho Vg, just rearranged. This rho V here are related from the definition of density. And after rearranging a little, this rho V is actually the mass of the displaced fluid. And so we get the force equal to mg, mass of the displaced fluid times gravitational field strength G, which is the weight equal to the upthrust. But which weight? The weight of the fluid displaced by the object immersed in it. Alright? So that's it. We just reversed the idea presented earlier. We just did the derivation of Archimedes' principle from the concept of pressure in fluids. Okay guys, bye.